Alright, welcome back to 3.5. We're on the last video for rational functions. We're going to start off with the rational function that intersects its horizontal asymptote. We ended with one that does not intersect it. Okay, so we actually have the same process, right? So step one would be to find the vertical asymptotes. Okay, so set the bottom equal to 0. Factor it. Will this be x plus 3 squared? Is that right? X squared plus 6x. Yeah. So x equals a negative 3. There's our vertical asymptote right there. Okay. Now for the horizontal asymptotes, we know that we could just take they're the same degree, sorry, so take the coefficients. So we know it's going to be y equals 2 over 1 or y equals 2. So that is going to be our horizontal asymptote. Right along there. Okay. Step 3. We want to find the y-intercept if there is one. So I plug in 0, right? F of 0 is going to be just fine. So f of 0 is going to be 0 plus 0 minus 4 over 0 plus 0 plus 9. So negative 4 ninths, super friendly number. So negative 4 ninths is like right there-ish. Okay, very specific. So now we know we have a point. Okay, we have the point 0, negative 4 ninths on our graph. That's very helpful. Okay. Now, we have to do a little bit more work, right? So step 4, again, let's go back and talk about the steps that we have here. Step 4 was to plot the x-intercepts, okay? So we take the top and set equal to 0. So we have 2x squared plus 3x minus 4 equals 0. What does that result in? So what do we want to do? Negative 8, 4 and 2, 1 and 8. So that doesn't factor, does it? Let's see here. Oh, it totally does. At 1. Well, if it doesn't factor nicely, let's just use the quadratic formula. So x equals a negative b plus or minus the square root of 9 minus 4 times 2 times negative 4 all over 4. So negative 3 plus or minus square root of 9, and then what is this? 16 times 2 is 32. So 9 plus 32 is 41 all over 4. Okay, that's a really nasty number. So it looks like looks like it's going to cross about right here. And because what root 41 is a number that is between 6 and 7. So this is negative 3 plus 6 over 4, so almost 0.75. And negative 3 minus 6-ish, so it's negative 9 over 4, so like negative 2-ish. There's the two spots it's going to cross. Yeah, a little more than negative 2. Okay, so those are the exact, you could put this into a calculator and get the exact number if you wanted to. But about right there. Okay, so we have all that information. We have the y-intercepts and the two x-intercepts. Okay, it stumped me I couldn't factor. I was shocked that they chose that example. Okay, step 5. Does it cross its non-vertical asymptotes? And remember, this is the whole point of this is, does it actually touch that? And so what we're going to do is we're going to take it and set it equal to our non-vertical asymptote, which in this case is y equals 2. So set it equal to 2. Okay, I do not have enough room to do this. Multiply it over, so let's do this. So we get 2x squared plus 3x minus 4 equals everything times 2. Okay, we can cancel the 2x squareds. Subtract over the 3x's, so we get 9x on this side, and subtract the 18, we get negative 22. So we get x equals negative 22 over 9. In other words, yes, it absolutely does go through it. Okay, so it will indeed go through the horizontal asymptote, which tells us a lot. Okay, so here's the thing. Step 6. We don't really need to do the whole table here. Okay, I need to know what happens over here, but we can actually infer what happens right here for the most part. Okay, and so let's go ahead and do it. So what's negative 22 over 9? That's approximately a little more than negative 2, probably close to this number. Okay? So let's see here. I want to plug in like -4 and see what we get. So f of -4 is 16, 32 minus 12 is 20, minus 4 is 16 on top. 16 over positive 16 minus 24, -8, so positive. So this is equal to a positive number. Okay? Don't care what it is, really. So we know where it crosses the horizontal asymptote. It crosses it at -22/9. So it's going to cross it over here somewhere. Okay? And so for this side over here, it has to look like this. Something like this. Obviously, it's just a sketch, right? Don't know exactly what it does, but it's going to go to this asymptote and go to that asymptote. It's not going to cross the vertical one because it never can, and it's not going to cross the horizontal one because we know it doesn't cross there. Okay? I don't actually have to do any more work on this next one. And here's why. I know it has to cross this horizontal asymptote at -22/9. It has to cross it. That's what the math tells us, right? So it has to cross over here somewhere, touch this, come up and touch this, right? Because this is your y-intercept, and go through this. And then we know it only touches in one spot, right? It doesn't touch the horizontal axis anywhere else. And so what this is going to do is it's going to come down, cross the horizontal asymptote at -22/9, where that's at. Go through our x-intercept, bounce back up. It's got to change concavity though, and go this way. Okay, so we had this point and we had this point right here, and that's all we needed. And that's because we knew exactly where it crossed our horizontal asymptote. We know it doesn't cross vertical asymptotes, and we had our two x-intercept and our y-intercept. So we don't need to make a whole table if not necessary. If we can infer any information on it, then we're good to go. Okay, so that's our graph. Kind of a cool one. My graphs are getting better though. They're not as ugly in camera. All right, so here's some behavior. So the behavior of a rational function near the vertical asymptote is always a little bit different. Okay, and so you notice that some of them go up, some go down. So if f of x is a rational expression in lowest terms, always got to be in lowest terms. If n is a positive integer, where this right here, x minus a, is a factor of the denominator, then the graph will behave in the manner illustrated. So if n is even, they're going to go the same way, either up or down. Okay? For example, we had that 1 over x squared look like this, right? They both went up. If n is odd, they're going to flip-flop. That was like the 1 over x example that we did, okay? This is just in general n behavior, so you can put that into your mental bank like we had the the x cubed n behavior and x squared n behavior. This just adds on to it, okay? All right, couple more examples here. So here is a rational function with an oblique asymptote, okay? So if you think back to our last video, we had example 4, which this is actually example 8. Think back to example 4, we found the oblique asymptote on that. And what was it? It was x plus 2. Okay? And so let's go ahead and just graph this. So the same 7-step process. Step 1, we're going to graph our vertical asymptotes. Pretty obvious, that's x equals 1, right? The more you do of these, the better you get at it too. Okay? Step 2, we know our oblique asymptote is y equals x plus 2. Okay, so this is where it gets a little bit different. So what we have here is we have to graph the line y equals x plus 2. So that looks like this, right? And then it's got a slope of 1. Trying to make it look really nice. I'm going to fail. Look at, I'm not the best artist. Okay, so we have our vertical asymptote, and then we have our oblique asymptote. So it's going to work exactly like the horizontal one, right? It's going to approach that thing and then move on from there, except for it's just a line now. Okay? All right, so step 3. Step 3 was our y-intercept. Plug in 0. F of 0 is 0 plus 0 over 0 minus 1. That's 0 over negative 1, which is 0. So we know it crosses at 0, which I already have that point plotted. Look at me. Okay? Well, f of 0 is 0. Hold on. 0 plus 0. F of 0 is... Oh, it has to cross right here. Just kidding. Not plotted. I just have a dot there. Okay? So the function has to cross there. This is just my line, my asymptote. So it can't be on that, right? So there's our x-intercept, or y-intercept. For the x-intercept, certainly we already have one. We just set it equal to 0. So x squared plus x equals 0. Factor that, x times x plus 1 equals 0, greatest common factor, right? So then we have x equals 0 or x equals negative 1. So it crosses at 0 and it crosses at negative 1, okay? I made those dots too big. So we have a little bit of a funky situation going on over here, but it's going to be fine in general, okay? So step 5, now we're going to see if it actually crosses our non-vertical asymptote, right? Because it can't cross the vertical one. So you take your function and you set it equal to your non-vertical one. So in this case, we set our function x squared plus x over x minus 1 equal to our oblique asymptote, which is x plus 2. Take x minus 1 on both sides. So x squared plus x equals, what is that? X squared plus 2x minus x. So plus x minus 2. And notice, this would cancel, and you get 0 equals negative 2. So sadly, no, it does not cross the non-vertical asymptote. So those two are both strict lines that we cannot cross. Okay? And so we actually have probably all the information that we need, but we'll do a little bit of work in step 6. I want to know what happens over here, right? So I want to plug in like 3, for example. So f of 3, what is that? 9 plus 3 is 12. 12 over 2, that's a positive number. Okay? Well, I actually want to know what it is, because is it down here or is it up here? That's kind of the question, right? So f of 3, what was that? I said it was 9 plus 3 is 12 over 2, which is 6. So it's positive 6. So it's up here. F of 3 is 6. So that tells us a lot, right? Because we have an asymptote here and an asymptote here. So up here, it's going to do this. Okay, kind of peel around like that. Now down here, it's going to have a mirrored image, right? But we have these two. And so we know it has to cross here, and has to cross here, and has to follow these asymptotes, so we just do this. That's all there is to it. Okay? So that is our function. A little bit easy. Oblique asymptotes aren't scary. It's just another line where it can't touch, right? So if it looks like I touched it there, that's just because I can't draw, not because I don't know the math. Awesome. All right, on to example 9. Almost done with this chapter. Graphing a rational function defined by an expression that is not in lowest terms. So this one's going to just be really easy, right? So this is where it gets a little bit tricky, because if you just attack this like the previous one, then you actually get it wrong, because it's a line. Okay? And so what you need to make sure you do is you need to make sure that every single rational function is in lowest terms. And so what I mean by that is, let's do a little bit of work ahead of time. This top part looks like we can factor. Let's do that. So we have x minus 3, x plus 2 on top, over x minus 3. Okay? So that's the equivalent to the function. Now, on top and bottom, we can actually cancel that out, and we get x plus 2. But here's the issue. In our original function, this is still like a remembered thing. This is still something that exists. And in this function, you cannot plug in, x equals 3. Because if you do, the bottom is 0, and that's no good. So what that means is that there's a hole, okay? So that means that there exists a hole, quote unquote, at x equals 3. So what you're going to do is you're going to graph the line, x plus 2, y equals x plus 2, but you're going to literally put a hole at x equals 3, okay? So x plus 2 is right here. It just goes up, boom, hole, boom, boom, like that, okay? That's your function. So what's important there is that we recognize that we could factor this and actually cancel. You might not be able to do that, and then you're back to the previous situation. Okay? But if you can get a nice function like this. This is just not continuous, right? I can't actually draw that without taking my pencil off, picking it up, and putting it back down, and going. It just means the function is not defined at x equals 3, but everywhere else it is. Okay? So that one's quite short. All right, and on to how we can use this. Okay? Not the greatest example. Probably parking ramps aren't super interesting to you. But it says vehicles arrive randomly at a parking ramp at an average rate of 3.6 vehicles per minute. The parking ramp attendant can admit 4 vehicles per minute, okay? However, since they are random, lines form at various times, right? We have surges, right? So maybe after a game or right before a lunch rush or something, okay? Looks like there's a source for this. Cool. All right, so the traffic intensity, X, is defined as the ratio of the average arrival rate to the average admittance rate. So determine X. So X is just going to be the average arrival rate, which is what? It says that they arrive at 3.6 per minute. And that's going to be over our average admittance rate, which is 4. So we have 3.6 over 4, which I believe is 0.9. I've been wrong before. That's okay. So that right there is our X. That's our traffic intensity. It's 0.9, whatever that means. Okay? And so the average number of vehicles waiting in line to enter the ramp is given by f of x equals x squared over 2 parentheses 1 minus x. So here's my issue with this question, right? Why? Okay? So that's just saying this can be modeled by that function. It doesn't really tell us why that's true, but that's what you should be thinking, right? But these rational functions come up all the time because that graph that we've looked at, that is how things grow on occasion. So evidently it's how these vehicles grow, where x is between 0 and 1, and that is the traffic intensity. Okay? So this evidently is true. I don't know who figured that out, but that's awesome. So we're going to compute the average number of vehicles waiting in line to enter our ramp. Okay? So all we have to do here is find out what f of 0.9 is. So you're going to plug that in, 0.9 squared over 2, 1 minus 0.9. I don't think this should be a parenthesis, though. I think this should be a squared, right? I'm not crazy. Nope, it totally should be just that. We're good. We're good. Okay? So you plug that in, and you end up getting 4.05 vehicles. Okay? So what's cool about this is if this is in general, if this is an easy function to find, say your dream, right? You're my PCA class, and your dream is to be a parking ramp attendant. If you can find that function easily in that source that's given, you can figure out what your traffic intensity, quote unquote, is, then you can know the average number of vehicles that are in line at any given time to figure out how long your loading ramp might be, which could be useful to you or not. Who knows? Okay? But that is the end of section 3.5. That'll cut out chapter 3. So, right? Yeah, because we're not going to do 3.6. So thank you for watching. Good luck on your exam. Have a good day.